All right, welcome. Today, we're going to put on our detective hats because we are opening up the Data Detective's Handbook. We're going to figure out how to properly investigate a set of data to make sure our conclusions are actually, solid. So let's get right into it. At the very heart of so much research is this one big question. Let's say you've got two groups and you see a difference in their results. But how can you be absolutely sure that difference is real and meaningful and not just some random fluke? Well, that's the central mystery we're here to solve. So, to crack this case, every good data detective needs a primary tool in their kit. Think of it like a special forensic device that separates the hard evidence from all the random noise. Our first mission is to really understand what that tool is and how it works. And here it is, the T-test. Honestly, just think of it as a super powerful magnifying glass. You point it at two different groups, maybe patients getting a new drug versus a placebo, and boom, it tells you if the difference in their average results is actually statistically significant. It is the absolute go-to tool for finding real differences. But, and this is a big but, here's the catch. You can't just bust this tool out and use it on any old evidence you find. Just like a high-tech piece of forensic equipment, it's really sensitive. To get an accurate reading, you have to make sure the conditions are just right. If you don't, your conclusions, they could be completely off base. So our first step as detectives is to profile the evidence, right? Just like an investigator carefully examines the layout of a crime scene, we need to understand the basic character of our data, what we call its shape or its distribution. And data usually comes in two main profiles. Over on the left, you see that classic, perfectly symmetrical bell curve, which we call a normal distribution. But on the right, you see something totally different, a skewed, lopsided curve. Trust me, these two shapes tell very, very different stories. Okay, so here's the crucial clue. In that perfect bell curve on the left, everything lines up perfectly. The average score, the middle score, and the most common score, they're all the same. But look at the skewed shape on the right. If you have just a few really, really high scores, they can pull the overall average way up, even if most of the data is down on the low end. That imbalance is a huge red flag that our data isn't normal. All right, so we've got the overall shape of the scene. Now it's time to zoom in on the details. We need to look for those unreliable clues. The bits of evidence that just don't seem to fit. In the world of statistics, we call these outliers. So what's an outlier? Well, it's basically a witness whose story just doesn't add up at all. It's a single data point that's so wildly different from everything else in the set that it immediately makes you suspicious. And why do we even care about these rogue data points? Because they have the power to completely distort the truth. I mean it. A single outlier can pull the average so far off course that it totally hides what's really going on, and it can lead you to chase the wrong suspect entirely. I mean, sometimes an outlier is so obvious it basically slaps you in the face. Imagine you're collecting data on how many times people went to the dentist last year, and someone puts down 90. Or you're recording ages, and you see an entry for 503. These are immediate red flags. Now, they might just be typos, but if you leave them in your analysis, they will completely wreck your average and point you to a totally false conclusion. So where do these weird clues even come from? Well, they can pop up from anywhere. Sometimes it's just a simple typo when someone was entering the data. Other times it could be an error with the equipment. And every once in a while, it might be something genuinely new and rare, a real discovery. The detective's job is to figure out which one it is. Okay, so we know our data needs to have a certain shape, and it needs to be free of these suspicious outliers. But how do we check this for real? How do we do it officially? Well, that brings us to the formal inspection. And you'd be surprised how easy this is in a statistical program like SPSS. You literally just navigate to the Explore menu and you check one little box that says Normality Plots with Tests. That one click runs the entire inspection for you. It's pretty cool. The first thing you get is this histogram, which is kind of like a visual fingerprint of your data. A normal distribution would look like a nice symmetrical hill. But look at this. See how most of the bars are all jammed over to the left, and then there's this long, flat tail stretching way out to the right? That's our visual proof right there. It's a classic, positively skewed distribution. Our evidence is not normal. The visual clue is strong, for sure, but a good detective needs hard proof. That's where this tests of normality table comes in. The software runs these formal statistical tests, and for our purposes, we're going to focus on the Shapiro-Wilk test to get our final conclusive answer. And here it is, the verdict. Just look at that number under the SIG column. That's called the p-value. Now, think of the p-value as the probability that our data could look this weird just by random chance, if it was actually normal. Our value here is 0.000. That is way, way less than the standard cutoff of 0.05. That's the statistical siren going off. It tells us without a doubt that the deviation from normality is real and it is significant. Case closed, the evidence is not normal. So, why do we go through all of this? I mean, why do all these rules and checks matter so much? It's simple. It's all part of the data detective's code. These are the 4 sacred rules for using that powerful t-test tool. First, the data has to be the right type, continuous. Second, each piece of evidence has to be independent. Third, you absolutely must check for and handle any significant outliers. And fourth, as we just saw, the data must be normally distributed. Today, we've really dug into rules 3 and 4. Look, following this code isn't just about getting the right answer for a homework assignment. It's about integrity. It's what ensures that when you finally stand up and declare a finding, that conclusion is honest, it's accurate, and it's built on a foundation of solid, sound science. So the next time you're faced with a spreadsheet full of numbers, remember to be a detective. Don't just analyze the data. Investigate it. Because who knows what incredible hidden stories your data might be waiting to tell you if you just know how to look.